Welcome to Algorush. Today, we're talking about how to build systems that just don't die. We're going to pull back the curtain on the blueprint for creating crash-proof systems that guard your data like a fortress, no matter what you throw at them. Because let's be real, in our world, losing data isn't just a headache, it's a disaster.
Okay, let's start with a simple, kind of terrifying question. Picture this. You're in the middle of some supercritical operation and poof, the power goes out. Everything's dark. What just happened to your data? Is it safe? Is it a corrupted mess, or is it just gone forever?
That sudden power outage puts two of the most sacred promises any system can make on the chopping block. First up is durability. That's the guarantee that once you save something, it stays saved, even if the building burns down. Then there's atomicity. That's the all-or-nothing deal. A transaction either happens completely or it's like it never happened at all. And a crash, well, it can blow both of those promises right out of the water.
So how in the world do we protect these promises? Well, the solution starts with a beautifully simple but incredibly powerful idea. We keep a log. This log becomes our absolute source of truth, the very bedrock of our system's safety.
This is called the write-ahead log, or WAL for short. You can think of it like the system's diary. It's an unchangeable, add-only history of every single thing that happens. And there's one golden rule, an unbreakable law. You write down what you are about to do in the log before you actually go and do it. This simple discipline is the secret sauce to recovery.
And here's exactly how that works. It's a strict 1-2-3 process you absolutely cannot break. First, you write the intended change to the log file on a durable disk. Only then, step 2, do you apply that same change to the super-fast data living in memory. And finally, you can turn around and tell the user, yep, we're all good. The operation is complete. That sequence is everything. And this right here really gets to the heart of it. The log has the final say, always. A transaction isn't really committed just because some code ran. Nope. It is only, truly, 100% committed when its final entry, its commit record, is physically safe and sound in the WAL on disk. Every log entry gets a unique ID, a log sequence number, or LSN, and that commit is only official when its LSN is permanent. Okay, so we've built a system that's rock solid and safe. Fantastic. But is it fast? And that brings us to the classic engineering tug-of-war, the constant battle between being perfectly safe and being ridiculously fast.
I mean, just think about it. Writing to a physical disk is painfully slow compared to zapping bits around in memory. If we had to slam on the brakes and wait for the disk to confirm every single little modification, our system would just grind to a halt. It would be safe, for sure, but it would be completely unusable.
So that's the million-dollar question, isn't it? How do we get the best of both worlds? How can we engineer a system that has those ironclad guarantees from the waffle, but without sacrificing the raw speed we need for basically any modern application? Turns out the solution is pretty clever.
The answer lies in taking some smart, calculated risks. Instead of being totally rigid, high-performance systems use two flexible policies to get that speed back. They're called steal and no force.
Let's break these down. The steal policy basically says, hey, I need that chunk of memory for something else, so I'm going to steal it and flush its dirty data, even if it's from an uncommitted transaction, to disk. It's all about managing memory efficiently. Then you have the no-force policy. This one says, you know what, we can tell the user their transaction is committed before we've actually forced all its data pages to the disk. This lets commits feel instantaneous.
Now, I know what you're thinking. That sounds pretty risky, right? Flushing uncommitted data, committing without flushing. And yeah, there's a price for all this speed. This table lays it out. When you use a steal policy, you risk having junk from failed transactions left on your disk after a crash. So you absolutely need a way to undo that mess. And with a no-force policy, you risk having committed data that only exists in the log. So you need a way to redo those changes and bring the data files up to date. Okay, so we've got our log. We have these fast but risky steal and no-force policies, and we know we need these recovery tools called undo and redo. How do you possibly combine all of that into a single, bulletproof recovery plan? Well, that's where Aries comes in. This is the ultimate blueprint.
Aries is basically the gold standard for this stuff. It's a recovery algorithm that was designed from the ground up to thrive in a world that uses steal and no force. Its whole job is to wake up after a crash, look at the absolute chaos, and systematically bring the system back to a perfectly consistent state, every single time.
And it does this with this absolutely brilliant three-phase process. Think of it like a detective arriving at a crime scene. First is the analysis phase.
The detective scans the log, our only witness, to figure out exactly who was doing what when the lights went out. Next, the redo phase. Now this is cool. The detective replays history, bringing the scene back to the exact state it was in at the moment of the crash. This includes reapplying changes from transactions that aren't going to make it. Finally, the undo phase. Now that the scene is perfectly set, the detective goes back and systematically reverses any changes made by transactions that never got to finish, leaving only clean, completed work.
So what makes Ares so robust? A few key ideas. It uses those log sequence numbers, the LSNs, to put a precise timestamp on everything. Critically, it always repeats history in the redo phase before it even thinks about undoing anything. This gets the system to a known, predictable state. And this last part is just genius. Ares actually writes log entries for its own undo actions. Why? So if the system crashes during recovery, it knows what it's already fixed and doesn't waste time undoing the same thing twice.
And that's the whole package. The write-ahead log is the foundation of trust. The steal and no-force policies provide the speed, and the three-phase Ares algorithm is the infallible cleanup crew. Together, they create a system that can honor those sacred promises of atomicity and durability we started with, no matter what happens.
So this is the blueprint for making a single machine incredibly resilient. But it really makes you think, doesn't it? This is all for one computer. What happens in our modern world of distributed systems? How do you guarantee these promises and prevent data loss, not just on one machine, but across an entire cluster of them?